Hi, welcome to module number 35. The topic is going to be logistic regression, and we're facing here a scenario where earlier we were performing classification by trying to model the probabilities, and sometimes the probabilities can be modeled as multivariate Gaussians, which we saw that can lead to LDA or QDA, and we can also have more sophisticated models such as mixture Gaussians. But what if we take another model? We'll look at log likelihoods and we'll model the log likelihoods as linear. So in particular, consider classes from perhaps 0 up to k minus 1, or alternately from 1 up to k. Really this is just a matter of convention. And we're going to define that the probability of being in class L conditioned on X, that probability divided by the probability of being in class K, and we're taking the log of the ratio, we're modeling it as beta L0 plus beta L transpose times X. Beta L is a column vector, therefore beta L transpose is a row vector, multiplied by X, a column vector, gives us a scalar. This scalar plus the DC offset beta L0, sum of two scalars is a scalar, so the log likelihood is a scalar. And again, this is not an equal sign, this is a modeling assumption. All right, this is going to be our model. So now let's evaluate the probability of being in class L conditioned on X. So the probability of G equals L conditioned on X is the exponent of the log of the probability of L conditioned on X. That's merely a definition. I took exponent of log. And this is the exponent of beta L0 plus beta L transpose times X plus a constant. Now, what is this constant? This constant is equal to the negative log of what's in the denominator, the probability of G equals to K conditioned on X. And we're going to incorporate that in a moment. In the meanwhile, what I want you to understand that the exponent of beta L0 plus beta L transpose times X, that appears in the numerator of the expression that we're trying to derive. As you can see here, we are showing that the probability of G equals L conditioned on X has this in the numerator, this expression that I just derived. This is my numerator, and I derived it. But what about my denominator, den? So I'm now going to open a new text box. And for the denominator, recall that we want all the probabilities to sum to 1. We want a sum over all the L's going from perhaps 1 through K, probability of G equals to L conditioned on X to be equal to 1. So now, let's set the denominator as a sum over L going from 1 to K, exponent of what we saw before, beta L0 plus beta L transpose times X. With this denominator, first of all the probabilities sum to 1. Secondly, they're all of the form derived earlier, namely what we derived for the probability of L given X, that we have an exponent of beta L0 plus beta L transpose X in the numerator, and we have something else. That something else is the denominator, which we just established a denominator that works well. What about the what about the latter expression? What about G equals K? In that case, in the numerator, we have basically exponent of, well, we don't really need anything in the numerator. We recall that we started with a definition of probability of G equals K given X, or L, divided by probability of K given X is a linear form. The linear form is now 0. If the linear form is 0, it tells us that the numerator will be 1, exponent of 0, instead of exponent of beta L0 plus, and so on. In other words, I'm really telling you that beta L0 plus beta L transpose X is 0, period. That's it. This also explains, if you look at these two expressions, the 1 plus correspond to M equals to capital K, and the other M's are treated in the summation. So we started with a model where the log likelihood was linear. From that model, we derived probabilities for all the classes, including this fixed class, the last class, capital K. So what's the hard part? You know, seems like we have a model, seems reasonable. The hard part is learning the parameters, all the betas. The book describes some details. Some of you may be interested in working on this for a project, and specifically putting together a classifier, a logistic regression approach, and implementing it, running it on data, and so on. So that'll be it for module number 35. We'll continue next time.